Thank you, Amanda. Hi, everyone. My name is Kurt Munson. I'm the engineering manager for HBM nCode, coming to you today from Detroit, Michigan. So welcome to all of you. Thanks for joining us. Good morning, good afternoon, good evening, depending on your time zone. We're going to spend the next 45 minutes or so looking at the question of how we create accelerated vibration tests, so durability testing in the frequency domain. How do we create shaker profiles that represent actual service loading? Or, secondly, we'll look at how do we compare existing shaker profiles with each other or with new measured service vibration data. So who are we? Again, my name is Kurt Munson. I'm an engineer with nCode. That's me, you can imagine, off in a cubicle somewhere. In turn, I imagine that's you guys, teeming throng of interested individuals. So with that level of interest from you, I'm going to carry on now, and let's get into the actual meat of our presentation for the day. The nCode software is made up of three parts: design life, glyphworks, and automation. The design life software is all about doing virtual durability calculations, predicting fatigue life from finite element stresses. Glyphworks, the application in the middle, is our focus for today, and this is for analyzing measured test data. The third application on the left is called nCode automation, and this is for maximizing the return on investment for measured test data, web-based data sharing, processing, reporting, and trending. We've had other webinars on design life and also on automation and other aspects of Glyphworks. Today we're going to focus on Glyphworks and one very specific aspect of it, the intersection of vibration and fatigue, what we call accelerated testing, shaker profile creation for random vibration testing, swept sine testing, sine on random testing, and so on. So on the left, on the right here is a picture of a device on test. This happens to be a charge air cooler pipe for a tractor. It sees vibration from a number of different sources, from field road roughness, also from the engine, also maybe from thermal effects. The predominant loading mode of this pipe is inertial loading. Because of that, durability testing on a pipe like this is often done on an electrodynamic shaker. That's the device that's seen in the lower half of the screen. This electrodynamic shaker can reproduce vibrations of specified frequency content. So the question is then, what frequencies are important? What magnitude should those frequencies be played back at? And for how long? Because we know from a durability perspective, number one, we want to prove the durability of this part so we can go to production. And number two, durability is driven by two main things: how many cycles occur and how big are those. So we need to think then our test spec is, how do we create an equivalent damage shaker test? We'll also move on then, secondly, to look at how do we compare different shaker test specifications. For example, which is more severe? Maybe someone says, we need to test this part with a swept sine test, maybe from 10 Gs to from 10 Hertz to 1,000 Hertz with a 1 G RMS or something like that. And someone else says, no, we prefer to do a PSD random test. So two different test specs, which is more severe. So the two use cases we're going to look at today is what I've got as number one and number two on the screen here. First off, how do we take measured vibration data, say accelerometer data for this pipe, and create a shaker profile as either a swept sine or PSD random or PSD sine tone on random? And secondly, how do we compare these different specifications? We'll look at how we do this live in software in just a few minutes. We can also use the nCode accelerated testing software to compare existing test specifications with measured service vibration data. This is a question that comes up often. Is the new vibration data more or less severe than the existing shaker profile? We can use the nCode accelerated testing software to answer this question. Without using fundamental fatigue and vibration principles, answering this question can become very difficult because the measured vibration data is typically in the time domain and the shaker profile is in the frequency domain. And there are difficulties in making direct comparisons looking at a PSD or a swept sine test and trying to understand its durability content relative to measured time series data. This is something we can do inside the nCode accelerated testing suite of software, and we'll look at that in just a minute. So this whole idea of creating accelerated tests or understanding the durability impact of existing accelerated tests is this. On the left side, we have to understand the durability content or the damage that's contributed from measured vibration data. Now, here I've got 3 different types of measured vibration. One is from the field called Belgian block. This is a particular maneuver on a car. The second event, working our way down on the left side, is called cross-country. This is the cross-country event, maybe in this car or in this vehicle, whatever the device on test is. So we have various ways in which these components are used. All of them create different vibration signatures or traces in the time domain, which of course represent different amounts of cyclic content. So we need to be able to understand in a cyclic way or in a damage sense, a fatigue damage sense, what's the impact of this cycling. If we can understand that, calculate fatigue damage, if we can do that, then we can move to the right side, which is to say, let's make a shaker profile that's somehow representative of that field service usage. For example, the test could be specified as a PSD random, or a swept sine, or a sine-on random, or a sine tone test. The idea, though, is that we want to have the same damage content as the measured vibration data, or what some people refer to as the mission profile, or the road load data. Furthermore, we want to accelerate this test to reduce test duration. We need to validate our design for longer and longer lives these days. For example, an exhaust pipe on a vehicle may be validated for hundreds of thousands of miles or even tens of thousands of hours of service. And it's not realistic for us to run a test over tens of thousands of hours. So our preference then is to create an accelerated test. But at the same time, we need to verify that we're not creating unrealistic loads by doing so. What we don't want to do is unrealistically accelerate a test by increasing its G loading, say its RMS loading, to the extent that we end up with different failure modes than the typical ones we've seen in the measured mission data. For example, if we have an isolated system, we don't want to have the G loading become so high that we have metal-to-metal contact. If that metal-to-metal contact occurs on the test rig, because the test is too far accelerated, and it didn't occur in the measured vibration data, then we can run into failure modes that change, and we end up with the familiar old scenario of the test runs, part breaks, and everyone says, well, that wasn't supposed to happen. I think we may have tested this wrong. Let's try this again. So we need to accelerate a test, but also do it in a sensible way. So that's the challenge for today is how do we create accelerated shaker tests with equivalent damage, but also reasonable in the same way. We don't want to turn measured vibration data into a series of crash tests, for example. The techniques we're going to talk about today come from 2 military standards, French military standard GAM EG13 and a NATO military standard AECTP 200. You can look this up and you'll find in there they talk about things like the shock response spectrum and the fatigue damage spectrum. Now we've taken these concepts and coded them up inside the nCode software. So from this point forward, we can focus on using the concepts of fatigue damage and equivalence and shock and frequency spectra and all these concepts. We can focus on using them as engineers, and we don't necessarily have to get into the dirty math behind the scenes. So here's a quick case study number 1, and I'm going to show you this live in just a few minutes using the nCode software, but I want to just set the scene to make sure we're all on the same page. In this case, this is an exhaust system. It used to be that exhaust systems were relatively cheap and could be replaced easily, and with more stringent emissions requirements, now these exhaust systems have gotten very expensive and heavy and need to last for a very long time. So ensuring their durability in a validation test is critical. The validation test that was going to be run here, you can see in the upper right corner, this is fixing the exhaust system on an electrodynamic shaker. And the question here is, what should this shaker reproduce? What frequency content? What magnitudes over that frequency bandwidth? And for how long? So in this case, measured data was known. So accelerometers were placed in the locations that were seen in the red dots on the left. And this vehicle was used in a variety of ways, various proving ground events or driving out on open roads or something like that, to understand vibration content. And then the nCode software was used with the concept of equivalent damage, shaker profile creation, to come up with the shaker profiles that we see in the lower left corner, or lower right corner. The green, the red, and the blue represent vibration profiles, G squared per hertz, a PSD random test, run in the X, Y, and Z directions. So blue, green, and red here represent X, Y, and Z. So in the end, the test is run the X excitation, one of these profiles, for the subscribed time period, maybe 30 hours on this axis, and then rotate the part, run it on the Y-axis for its prescribed time, and then likewise do that again on the Z-axis. So this way, then we have a field correlated or mileage or hours correlated durability test spec. So if part failure does occur, we can index that back to field service time or mileage. And then if we pass this test, it's not just a random bogey test. We have something that's actually correlated back to miles. So this is a good thing. So I'm going to explore this in more detail in just a minute using the nCode software. Before I do that, though, I just want to talk about a second use case, and that is not so much to create a shaker profile, but rather to work with an existing shaker profile. So we have this comparison question of supplier A says run a swept sine test, and supplier B says no, we ran a random vibration test. And the question then is, if you pass one and fail the other, what does that mean? Or if they both pass, what does that mean? Which test was actually more severe, in what sense? So in this case, we want to compare with an existing shaker spec. So here in this slide I've got, this is the device on test is the red underslung storage device. Excuse me. And it sees vibration from a number of different sources. It sees vibration from wind loading, aerodynamic buffeting, flutter, and so on. So the question is, can this device last on this jet fighter? So on the jet fighter, an accelerometer is placed on the mounting bracket that holds this underslung storage device on, and we have measured vibration data in blue. So that will help us understand how severe that environment is. So we can see here then, we'll calculate this thing called the fatigue damage spectrum. And we'll look at this in more detail in just a minute. This is like a frequency spectrum, but now the vertical axis is in fatigue damage, or severity of accumulated cycles, plotted versus frequency. So this allows us to understand how severe is the mission. The next question is, this particular underslung storage device was actually previously tested for another aircraft. The exact same storage device, exact same bracketry, was tested for a low-speed aircraft. And the test that was done, we can see that shaker profile in the test rig in the lower left corner. So we know for a fact that this device, this underslung storage device, passes this random vibration spec for, say, 30 hours or whatever the service life was. So we know that it can pass one test. That's the lower left corner, the existing shaker profile. The question is now, is the new vibration data up at the top more or less severe than that? If we use this concept of the fatigue damage spectrum or the fatigue damage transform, now we can look at these very disparate pieces of data, one in the time domain, one in the frequency domain, neither one purely a durability metric. We can both convert them into this fatigue damage spectrum. These are the plots that we see in the middle of the page, and we can compare then the test envelope or design envelope in red. Is that more or less severe than the accumulated fatigue damage from the flight data at the top? And we can see from this then, by comparing these fatigue damage spectra, that the design envelope or the test that's already been passed is more severe in a fatigue sense than the measured flight data on the new aircraft. Therefore, we have what's called read-across evidence, or more colloquially, you might call this grandfathering. We can say that since it's already passed a test that's more severe than what it's going to see now, we don't need to rerun testing. We can, based on engineering inference this way, or read-across evidence, we know that this thing will not fall off this new aircraft environment. So yes, read-across evidence says this thing will survive. This pays dividends in terms of less testing to do and quicker validation in the process. So I'm going to take a look now, do some of this live. We've talked a bit about the concept of creating accelerated shaker profiles or comparing existing shaker profiles. And I want to do that live now using the nCode software. So I'm going to jump in over here. And this is what we call nCode GlyphWorks. A number of you guys already use nCode software. If you don't, just a quick introduction. We have these functions in here. These icons are called glyphs. It's short for the term hieroglyphics, like the Egyptian symbolic representation of something larger. We call these boxes, we call them glyphs, and that's where the name GlyphWorks comes from. We have about 100 and some odd glyphs in GlyphWorks now. Some of them are related to vibration analysis, some statistical, some fatigue, some crack growth related, so on and so forth. I'm going to focus on just a few of these glyphs today because a subset of these glyphs are what we call accelerated testing and are useful for the exact subject matter for today, which is this shaker profile creation. If you want to know more about other glyphs in GlyphWorks, take a look on hbm.com/ncode, and you'll see recorded webinars that cover GlyphWorks in a more broad sense. But we have a very specific mission today, and that is to understand this. We have some time series data here. So what we have here, I've just dragged out of this available data window. So this is time series data that I've dragged and dropped into the input area here. This creates my first glyph. This glyph here shows me 3 channels of data in the time domain. You might call these channels or traces or signals. This is acceleration in the x direction, y direction, and z direction versus time. This is from a 4-wheel ATV, off-road vehicle, and the challenge here today is that a new headlamp assembly, a new lighting assembly, is being proposed for use in this ATV, and the headlamp will see a variety of different vibration sources, both from rough road and from engine vibration and so on. And that engine vibration and road vibration and such is characterized or understood by using an accelerometer, in this case an X, Y, and Z, triaxial accelerometer in this location. This would be at the, say, the bracket that holds the lighting assembly on. So this is G's versus time, and this will help us understand how severe is the measured environment for vibration. So we can use these glyphs in GlyphWorks here to do all sorts of different types of calculations. For example, if I wanted to, I could calculate a frequency spectrum directly on this time series data. Now the challenge is, if I look at the frequency spectrum, that's a very useful thing, but it doesn't truly capture durability. And that is because if I have 1 lap of my proving ground, or 10 laps of my proving ground, or 100 hours of vibration, or just 10 seconds of vibration, I can come up with the exact same frequency spectrum. The frequency spectrum is inherently non-cumulative, whereas we know that fatigue damage, fatigue problems are inherently cumulatively building towards a problem. So the frequency spectrum glyph can be useful, but it's not going to help us here if we're truly interested in durability. What we're going to use instead is this concept of the frequency shock response spectrum calculation. And this will give me 2 outputs, the shock response spectrum and the fatigue damage spectrum. So I'm going to go ahead and calculate these, put on a couple of display glyphs to capture these answers. Duplicate this one, this down here like this, and just as a naming thing to keep these straight, I'm going to call this top one and rename this glyph to call it shock. And then this bottom one, it said was the output was the fatigue damage, so I'm going to call this fatigue. Okay, so now I'm going to go ahead and run this process. And a couple of lights came on there very briefly. And what we end up with then is the time series data has been passed into this glyph called the shock response spectrum. And it's enabled the calculation of 2 things, the shock spectrum and the fatigue damage spectrum. So I'm going to start with this one up at the top here, the shock spectrum. So we had 3 channels of acceleration, From this point forward, we're going to do all of our calculations separately. The X channel, the Y channel, and the Z channel will all be used separately. And the reason why we do that is because that's the way typically this type of testing is done. Typically, the testing that we're going to do is we're going to shake in one axis, followed by shaking another axis, and followed by shaking in the third axis. So a sequential playback, you can say, of vibration. So we're going to mirror that, do all of our calculations on separate channels. Our end goal here is to create an accelerated shaker profile separately for X, Y, and Z directions, and then we can then use this as a table of breakpoints for our shaker test. So this is what we call the shock response spectrum for the first acceleration channel. This is the worst case G loading as a function of frequency. So in a way you can think about this, if you're used to the fast Fourier transform, you could think about this as the fast Fourier transform with a peak hold turned on. Now it's not exactly that, but that's the idea. The idea of a peak hold is that we're getting the worst case vibration magnitude as a function of frequency. Now this is often used for designing electronic parts. For example, your cell phone. What's important in a cell phone is that you should be able to drop it and pick it back up and it still works. And you drop it again and you pick it back up and it still works. Now if you did that 1,000 times, shame on you, and you wouldn't expect it to work. However, you expect it to be able to withstand peak G loading a few times. If that was your design metric, the shock response spectrum, the worst case G loading versus frequency can be a very useful design metric. Now, but what about the accumulated, not the worst case, but the accumulated fatigue damage, the fatigue side of inertial loading? That's down here. This is what we call the fatigue damage spectrum. Put this on a logarithmic plot and we can see better. We've calculated now, again for 3 channels, X, Y, and Z vibration separately. I'm going to look at just one at a time. As a function of frequency, now we have what's called damage. So this is our fatigue damage metric versus frequency. If you've been around durability before, you may have heard the term damage. If not, let me explain a little bit here. Fatigue damage means how much of the life is used up. So we'll take a look in just a minute. We'll go back and understand an SN curve or a fatigue property set or something like that. We'll get to that in just a minute. But the general idea here is that we've taken the input measured time series data, which has cycles of inertial loading, which would cause cycles of inertial stress. Cycles over time cause fatigue damage or use up fatigue life. We've just got a metric of that now. This is fatigue damage on the vertical axis, plotted versus frequency. These numbers here are not global. You may have heard of, in the durability sense, that Miner's rule equals 1 is failure. We are not using strain gauges or real true stresses here, so there's no global relevance to these numbers. This is just a, you could say, kind of a blue to red scale, if you're thinking about a finite element model with stresses, or a cool to hot kind of a temperature scale. But regardless, this is accumulated fatigue damage over the measured time domain as a function of frequency. The way these calculations were made, we can look at here by going to the properties of the shock response spectrum glyph. We have a number of properties in here. For example, over what bandwidth are we interested? Maybe we want to control our test rig, say, from 5 to 100 hertz. We also have some other things down here, some properties related to fatigue settings. What are the, what's the SN curve slope, for example? We're doing what's called like a pseudo-stress fatigue calculation. So if you want to control slope and intercept parameters for the SN curve, this is the place you do so. We also have some dynamic or vibration settings in here to look at the amount of damping or dynamic amplification in the system, and so on. The thing I want to focus on here is looking at, let's assume that we need to replicate 2,000 laps of time series data. Let's assume that the input time series here is 1 lap of my proving ground on my ATV. In the actual durability life calls for 2,000 laps of that. In other words, my lab test needs to be equivalent to 2,000 laps of that time series data. So I can say I want to calculate the shock and the damage from 2,000 repeats. Click OK to accept that. Rerun this process. And now what's changed is the fatigue damage spectrum has gone up by a factor of 2,000. This is Miner's rule in action. It says that if cycles continue to happen, more and more damage could accumulate. As a matter of fact, if you were to go out and continue to run around the proving ground continuously, and you were to monitor the fatigue damage spectrum over time, you'd see that these levels would continue to go up and up and up and up and up in a way that represents the accumulation of fatigue damage, and also in a way that a frequency spectrum, a straight PSD or frequency spectrum, doesn't. So this is highlighting one of the benefits of looking at this in terms of fatigue damage. We can understand the difference between one customer saying, we need this validated for 2,000 laps, and another customer saying, no, this is an extended duty cycle. Give me the shaker profile that represents not 2,000 laps, but 3,500. A different customer has a different demand for the design target. So that means then the validation test needs to become more severe. All of this severity concept is shown quantifiably in this fatigue damage spectrum versus frequency. So what I've done here now so far is quantified the severity of mission or measured data in two ways, in terms of shock and in terms of damage. If the part is designed solely with durability in mind, the fatigue damage spectrum is very important. If it is designed solely with shock in mind, then this is very important. This is your iPhone, for example. It's designed to be shocked, dropped, or abused a few times, but as I said earlier, shame on you if you expect to drop it 1,000 times and continue to work. So I've quantified mission or measured data severity. The next step is to come in here, and I'm going to use a glyph this time called test synthesis. And what this means is give me a shaker profile that's equivalent to this amount of fatigue damage. This is fatigue damage accumulated over 2,000 laps. So I'm going to ask this test synthesis glyph to come along and tell me what shaker profile would produce that much damage in a far shorter time period. Rather than running around for 2,000 hours, maybe I want to run a test for, say, 10 hours on the shaker rig or 20 hours on the shaker rig. So the output of that glyph, the test synthesis glyph, right here is another two-dimensional thing. This is the PSD. This would be the shaker profile. So I'm going to rename this shaker profile like this, and I need to tell the test synthesis glyph a few things. For example, really critical input here is what's the duration of my shaker profile test going to be? I'm going to try running a, let's say, a 15-hour test. So the magnitudes of the shaker profile should be calculated such that in 15 hours of that GRMS profile, I produce 2,000 laps worth of fatigue damage. So let's take a look at that right now. Rerun the process, and what we have now in terms of shaker profiles, we have 3 separate shaker profiles on a log scale. They look like this. You can see this is the X, Y, and Z vibration, separate profiles. Let's look at just one at a time for simplicity. So this is the familiar table or plot of G squared per hertz versus frequency. This is the equivalent damage shaker profile. So the kind of things that the test lab guys get interested in now is things like, what's the GRMS level? So I'm going to put on another glyph for that. Also on here, how do I get this? If this is my equivalent shaker profile, I need this as a table of breakpoints or numbers that I can use for my vibration controller. So I'm going to use another glyph here called data values display. And what we end up with then, when I rerun this, is the same information as before, but now you can see we have things like over here. This is my shaker profile. This is the spectral RMS. So what's the GRMS level for each of these shaker profiles for X, Y, and Z directions? And then lastly, down at the bottom here, this is my table of actual breakpoints. Instead of graphically showing me what's the G squared per hertz level, as I've shown in this picture, now we have the same information in a tabular form. And notice this has an export or copy. So as we say, all roads lead to Excel. Everybody wants for shaker rig control, this table of breakpoints in Excel or some typical, like a spreadsheet like that. That's why we have these export and copy buttons. So what we've done here, I'm not done yet, but just to review what we've done, we've taken the measured time series data, quantified its severity in terms of shock and fatigue, and then turned around and said, let's make an accelerated shaker test. I used some number of hours, I think it was 15 hours. And as a result then, here are my 15-hour shaker profiles given to me in terms of a tabular display, a graphical display, and also looking at some statistics like spectral RMS. Now, the next question that comes up, I said before earlier that it's important for us to keep tabs on how severely we accelerate a test, because if I'm not smart about things, I might come into this glyph here and say, you know what, why do we run a 15-hour test when we could run a 10-minute test or a 1-minute test? And GlyphWorks, any math, will be happy to return a shaker profile that creates equivalent damage in that prescribed amount of time. Now, we know from an engineering perspective, at some point, the shaker magnitudes will get too large, either 1 for the test rig or 2 for our part, and we'll end up with different failure modes and things clanking around and hysteretic heating of rubber parts and so on. So what we need to do then is realize that this test duration here, the number of hours I use here, is a key independent variable to defining this test. So we need to assess whether this independent variable, this test duration that I've chosen, we need to make sure that this is sensible. And the way we're going to do that is by using another glyph here. It's called the extreme response spectrum. And it looks very much like the shock response spectrum in that it calculates the fatigue damage. It also calculates this thing called the extreme response. The main difference between these two glyphs is that this one has a time series input. It's for measured vibration data. Whereas this one down here has a PSD input. What I'm getting at here is I can take this accelerated PSD, plug it in here, and I can turn on and calculate the same two things I used to quantify shock and damage from the measured data. I can do that exactly straight in the same way for my shaker profile. So this will allow me to test, is this test really equivalent damage? And is it reasonable shock? So I've got to do a little bit of plumbing here, connect a couple things together. This will make a little bit more sense when we run this process. So just bear with me while I set up some plumbing here. Okay, so essentially this glyph and this glyph are doing the same operation, just one of them is doing it on the measured time series data, the other is doing it on the new proposed shaker profile. For the new proposed shaker profile, I need to set it up over the same bandwidth as we looked at before, and also I said that my shaker profile is going to run for 15 hours in each direction. So I want to replicate 15 hours of this new PSD random vibration. Run this process as I did before. Exact same shaker profile, exact same spectral RMS, and so on. What's new is if I go look at fatigue damage, I should have two fatigue damage plots here now. So we've got two. I'll look at them separately. So we've got fatigue damage from the measured time series data and fatigue damage in the bottom plot here from the proposed shaker profile. We'll look at these together, and you can see that their magnitudes are the exact same. If I overlay them, we actually see they're coincident, so I only see one. This is my proof, my quantifiable proof that the test that I've created is equivalent. 15 hours of shaking that way is equivalent to 2,000 laps of measured proving ground data, equivalent in a fatigue damage sense. Okay, so this is a good thing. I'm using fatigue damage, this accumulated concept of cycles and size and Miner's rule and all that. That's a good thing for durability testing. And I'm using that then as my metric for what test should I create. So this is a good thing. What's also interesting up here is if I go back now and look at the other metric, shock, peak G loading. These are not exactly the same. As a matter of fact, here I can see that this is the one from the measured proving ground data. and the blue comes from the new PSD test, we can see here, if I overlay them, that the peak G levels to get accumulated damage to a certain level in a prescribed 15-hour time period, the peak G levels are actually quite high. So it's not necessary for these two to line up, but this is a good metric to say that it looks like the peak G loading is increasing by about a factor of, almost a factor of 2, it looks like, in this frequency band. So if we had parts resonating in the, say, 20 hertz, sub 20 hertz range, the peak G loading that we see in this accelerated shaker test is about twice as high as the peak G loading seen in the field. Now, if that raised concern about, say, an isolation joint not behaving the way it should, or causing hysteretic heating in rubber, or metal-to-metal contact, then what I could do is I could come back in here and say, actually, I should increase my test duration to maybe, let's do 30 hours per axis. And let's model the fatigue damage and the shock from 30 hours of that shaking. We can rerun this. You notice the spectral RMS values have gone down a bit. The shaker profile, G squared per hertz, has gone down a bit as well. And you can also see that the peak G loading has gone down as well. So we have this kind of sliding scale of, obviously you can imagine, the shorter the test is, the higher the GRMS, the higher the G levels, and so on are. And we can reference that to the measured proving ground data to try to get a feel for how severely can we accelerate this test. Obviously, we'd expect to see peak G overloads if we're really truly creating a highly accelerated test, but to keep this within bounds is a necessary way to ensure that we don't end up with just a plain straight halt test, for example, where the idea is just to break things under extremely accelerated shock levels. Okay, so what I've shown here is a process by which we can take measured proving ground data and then create a shaker profile and also export that data, say, to a third-party app like Excel. The last thing I'm going to do here before I leave this is save this process. All the glyphs I put on here and the time I've invested in clicking and changing properties and such, I can save. So I'm going to call this create shaker profile. This is being saved as what's called a workflow or a nCode GlyphWorks template. So I can come back and reuse this. All the glyphs, all the properties and such are maintained. And it's like a template, and I can put more data into it in the future and rerun. And this way I can capture the intelligence and the time that I've invested and reuse it in the future. All right, so that was looking at use case number 1. How do we take measured vibration data and convert that into a shaker profile that can be reasonable? Now, the shaker profile I've been looking at here it was a PSD random. We can certainly extend this as well into PSD random plus a sine tone or a sine sweep. Like a sine sweep on random is a popular thing these days, and so on. We have techniques for dealing with that. For time, though, I'm going to omit that. A swept sine is another option. A lot of people test parts these days with swept sine or even swept sine on random. We have ways of dealing with all these different shaker profiles, but I'm not going to get into them in detail right now just based on time. What I do want to show in the second application here is how do we deal with comparing with an existing spec. So it may not be that you want to use this vibration data to create a new spec. You may not even have the leeway to do that. It may be that your remit as an engineer is to run someone else's shaker profile, a specified profile. But the question comes up then is which one is more severe? If you've been using an existing shaker profile, say for the last 20 years, we use the SAE battery spec or maybe the MIL Handbook 810G spec for electronic components. The question often comes up, that spec has been around for a while, but do we really know how severe it is? So I'm going to take this concept of severity. Let me get rid of a couple glyphs here. And rather than creating a new shaker profile, I want to compare that vibration data with an existing profile. And that leads me to the use of this glyph, called the vibration generator. The vibration generator allows me to type in a table of breakpoints. So I can say I have a PSD test, for example, that maybe runs 0.1 G squared per hertz from 5 to 25 hertz, 0.1, and then it ramps down out to, at 50 hertz, it goes to 0.01, and then at 100 hertz, it's dropped off to 0.005. Okay, so just a simple table of breakpoints. Often these existing standard specs are maybe 5 or 8 breakpoints in kind of a blocky looking frequency spectrum. And I'm just going to type in those numbers here. We can also import them from a spreadsheet as well if that's easier. And I'm going to call this the existing SAE spec. Okay, so this is essentially building up just that table of breakpoints. And like I said earlier, I want to quantify the damage that comes from that. So just like we quantified the shock and the damage that comes from the measured data, I'm going to do the same thing again now with the PSD test. So I look in the properties here from 5 to 100 hertz, and let's say the existing test spec says we need to run for, let's say, 24 hours per axis. And we're going to compare that with 2,000 laps of the vibration data we see up above. So this creates the kind of things we looked at before. Put a couple plots together here and run this. And what we get then is these fatigue damage spectra. Make this a little bit bigger this way. These fatigue damage and shock spectra show us some interesting things. The fatigue damage spectra down at the bottom, if I overlay them like this, this shows me this is the blue is the existing SAE specs fatigue damage accumulated over 24 hours. Whereas the red is the accumulated fatigue damage for 2,000 laps of the measured input time series data. So we can see very quickly from an accumulated fatigue damage sense, especially if I zoom out a bit, we can see that the fatigue damage is an order of magnitude or higher from our existing spec. So this helps us quantify or understand in a vibration sense and also in a durability sense. How have we been testing all along in a fatigue sense relative to the actual vibration that this part sees in the field? Similar information is seen up at the top here. This is the G plot that says G's versus frequency, so the worst case G loading versus frequency for the test spec versus the measured proving ground data. So this can be very useful when Volkswagen comes and says, you need to test your part with a swept sine test, 5G RMS, flat spectrum from 1 to 200 hertz. And then Nissan comes along and says, no, you need to test your part with a sine on random or with a PSD random of a certain profile. And you run those two tests, and the question may be then, do we really need to run two tests? Why don't we look at the severity of the two and run the test that's more severe? Use that going forward. All right, so this is all I'm going to show right now for this second use case, comparing severities of different profiles. But this can be a very powerful thing because it's really, really difficult in a traditional sense to compare a swept sine profile versus a PSD profile. The statistics are inherently different. The processes that are represented are inherently different. A PSD random says all these different sine tones are being played out simultaneously, so we get bigger cycles from them, whereas swept sine doesn't. But if we look at the fatigue damage concept, that allows us to understand cycle size, numbers of cycles, fatigue damage accumulated over time, and so on. And we can get some really good quantifiable metrics out of this. So having said all that,